Assalamualaikum and a very good day to everyone. So today we will continue our discussion on MOSFET, which is the last topic for MOSFET regarding on the AC analysis. So here are the learning outcomes that you should learn in this topic, which you should know how to conduct the AC analysis on linear applications of OPM. Alright. So these are the hybrid pi model. Okay, so same as BJT. Okay, so if we can recall back what we have learned in BJT, right? So in BJT, all right, so this is BJT of NPN, which here is the base, collector and emitter. So in AC analysis, all right, which is the hybrid pi model. Okay, the hybrid pi model will be, here is your base, right? The base, this will gonna be your R pi, and this will gonna be your V pi, and this will gonna be your emitter, since that the emitter is straightly goes to ground. Okay, so here will gonna be your emitter, all right? And then here will be your transconductance, which is the GM V pi, right? And parallel to that, we're gonna have R naught. And here is your collector junction, right? Okay, so this is the hybrid pi model. Okay, this is the hybrid pi model for BJT, all right? So same goes to the MOSFET, all right? The hybrid pi model for MOSFET, which we will focus on NMOS, all right? Yeah, we will focus on NMOS. We're gonna have the gate, drain, and source. So for the hybrid pi model, okay, so you can see, right, at the gate, okay, gate, always remember for MOSFET it is the voltage control device, right? Device, CE, right? Where for BJT, this is the current control device, right? Okay, so therefore between the gate and the source we have the voltage, okay, for MOSFET, right? But between for BJT, between the base and emitter, we also have voltage, but the one that is controlling your BJT to be functioning is the IB current, right? But for MOSFET, the one that is controlling the MOSFET is working or not is the voltage between the gate and the source. So you can see the hybrid pi model, okay, they're gonna be a gate. Always remember this is fixed, yeah, the hybrid pi model is fixed. Here is positive and here is negative. This is your gate, this is your source. Between the gate and the source, right, between the gate and the source, we have VGS, voltage between gate and source terminal, yeah, all right? And then same, okay, as BJT, we're gonna have a transconductance. So here also, sorry, okay, so here also we're gonna have a transconductance, which is GM VGS. In BJT we have GM V pi because across the transconductor we have V pi, so therefore at the collector we have GM V pi. But for for MOSFET, all right, the voltage across, I mean the parallel voltage to the GM or the transconductance is VGS, therefore it will gonna be GM VGS, okay, GM VGS. And then it's gonna be the drain, here is the drain, and parallel to that we're gonna have RD. So what is RD? Okay, RD is the internal resistance between the drain and the source terminal. Okay, alright. So we are not considering the PMOS. Okay. Next, here are the mathematical formula that you need to remember for the AC analysis of MOSFET. Okay. So what is GM? Okay, as we have learned in BGT, GM is a transconductance, and some reference book you might found it is written as GFS, so it is actually the same, yeah, GM or GFS, but in our syllabus we usually we're gonna use GM. All right. And what is GM? GM shows how effective the gate voltage is in controlling the drain current. Okay, so it shows how effective the gate voltage in controlling the drain current ID. So the unit for GM is Siemens, yeah, S, which is symbolized as S, but we called it as Siemens. So here are the mathematical formula that you need to remember, or we gonna use frequently in analyze the AC analysis in MOSFET. First of all, same as this. This is same as DC analysis MOSFET formula, right? Which is to find ID is equals to K VGS, which is okay, the product of VGS minus the threshold voltage squared of it. Okay, and what is K? K is equals to ID on divided with VGS on minus V threshold squared, right? So this formula is the same as what we have learned in DC analysis. Okay, you still use this formula for AC analysis. All right. So next, the another formula that we you need to remember, which is this is the new formula which only appear on AC analysis, is how to find the value of GM. Okay, so GM can be calculated is equals to 2K, all right, which this K is same as this K, all right, this K is same as this K. So how to find this K? You can still use this formula, all right. Okay, multiply with the product of VGS minus the threshold voltage. Okay, voltage at the gate and source minus to the threshold voltage. Okay. Next, another formula for GM. Okay, because sometimes the voltage is not given to you, so therefore we can rewrite the equation of GM to be GM is equals to 2 set of KID. So you have two methods or two formula to find GM, which one you are using the voltage, which is the difference between the voltage at gate and source minus with the threshold voltage. But let's say the voltage is not given to you, we actually can rewrite this equation, right, to be as such, which is 2 set K, which is the constant value, okay, which K can be found by using the ID on or VGS on minus VT, which is the threshold voltage set, and you divide both of them, okay, multiply with ID. So set K that is multiplied with ID. All right. Okay, so always remember, yeah, this the asterisk formula that I've marked here. All right, and always remember this formula as well. Okay, all right. So now what is RD? Okay, where is the RD? Okay, let's rewrite again the hybrid pi model. So the hybrid pi model is, this is your source, this is your transconductance, and this is your drain, this is your internal resistance that is called as RD. Okay, so between G and S, gate and source, we have VGS, and this is positive and this is negative. Alright, and this is GM VGS. So what is RD? RD is the output resistance. So output resistance of RD is located between drain and source. Okay, because we know the drain and source for MOSFET. Okay, this is our MOSFET, this is the source, and this is drain. So drain and source is our output, gate and source is our input. Okay, so it's located between the drain and source terminal. Okay, so usually it is very large in value. So as what we have learned in BJT, if the value of RD is very large, for example infinity, what it gonna be? It will become open circuit. So of course current cannot pass through this resistor, right? So if the value is very large, your hybrid pi model will be as such. This is your transconductance, this is your drain, and this is your source. Here is your VGS, here is your GM VGS. So if RD is infinity, so it will become open circuit. Okay, RD will become open circuit. Alright, and in this case you can neglect the RD value during your AC calculation. Okay, but sometimes if the RD is not infinity, alright, you need to calculate lah. Okay, so RD can be calculated by using this formula. Yeah, the difference, okay, between VDS, okay, slight difference in VDS between the drain and source voltage, divide with the difference of ID, drain current. Okay, and the unit is ohm, voltage divide with current, so the unit of RD is ohm. Okay, but usually in our cases, most of the cases, RD is very large in value, and therefore you can consider RD as infinity. Okay, always remember, in our calculation, in our circuit analysis, RD is very large in value, so it will become open circuit. So therefore your hybrid pi model will look as such. Alright, so what are the steps to analyze our AC analysis in MOSFET? Okay, so first of all, you need to analyze circuit with DC sources only. Okay, alright, first of all, of course, we need to start the calculation with the DC source, which you need to find the value of K if it is not given to you, and what else? You need to find the value of ID if it is not given to you. So both of these you need to calculate. Alright, but if it is provided to you, then you can just straight away solve it. Alright, okay, so in DC analysis, okay, we need to replace all the capacitor as open circuit. Okay, as open circuit, and then we need to determine the Q points, yeah, the IDQ, the VGSQ, and this VDSQ. Alright, and then this is for your DC analysis. Okay, next, with the value of IDQ, VGSQ, VDSQ, the value of K and the value of D, we can proceed our calculation with AC analysis. Okay, which for the AC analysis, we only focus on the mid-frequency range. Alright, so how to solve the AC analysis? First of all, we need to replace the DC voltage source with short circuit and ground it, meaning that it's same as BJT, where all the DC voltage source will become ground. Okay, it will become ground. And then we replace the coupling and bypass capacitor with short circuit. Okay, all capacitor will become short circuit. So it's differ. If it is DC, all the capacitor will become open circuit, right? But for AC, all the capacitor will become short circuit. Alright, so this is same as BJT. And then we need to replace the transistor. Okay, so in this case, the transistor is MOSFET with equivalent model of hybrid pi model. So how is the model is? So the model is, here is your G. Please remember this model, okay? Because this model is fixed. And then you're going to have transconductance, and then you're going to have drain, and then this is VGS, and this is GM, VGS. And usually the RD is infinity. Okay, next, analyze the small signal equivalent circuit. Then we need to analyze the equivalent circuit. We need to develop the equation from the general amplifier model and calculate the desired amplifier model parameters. Okay, so later we're going to look what is this all about. Right, so now let's look into the next slide. Okay, so first of all, okay, if it is given this circuit, okay, so we know this circuit, if you look at the input, where is the input? Gate is your input. At your input, we have two parallel resistor, R1 and R2. So we know this is actually a voltage divider bias. So to analyze this circuit, okay, you need to proceed with the DC equivalent circuit. So how? In DC equivalent circuit, the capacitor, all the capacitor will become open circuit, right? Will become open circuit. So in that case, in DC equivalent circuit, the capacitor will be removed. Here will be removed. So if it is removed, in this case, you're going to have, or the circuit will leave behind as such. You're going to have R1, you're going to have R2, you're going to have VDD, RD. Okay, this is the drain terminal, the source terminal, and we're going to have RS, and this is our gate terminal. Okay, so these were going to be your DC equivalent circuit. How about our AC equivalent circuit? So AC equivalent circuit, remember your capacitor, there are two rules, right? Your capacitor will become short circuit. This is the first one. And the second one, your DC source will become ground. Okay, so in this case, where is your DC source? Here is your DC source, right? This is your DC source. So here will become ground, and here will become short circuit. Here will become short circuit. If this is short circuit, what will happen to your RS? RS will be removed. Okay, so meaning that no current will pass through RS. Instead, all the current will pass through to this capacitor. Okay, alright. So therefore, okay, your circuit will be, okay, let's draw the circuit V in. So the capacitor C1 short circuit. So this is your capacitor C1 short circuit. Next, it will go to this junction. So at this junction, this is the point. Okay, this is the capacitor just now, right? So this is the point, and it goes to the arc. Okay, I make it down. So this is your R1, and after R1, it goes to ground. So I make the ground at the bottom. Next, at this junction, we still have R2. So goes to R2. So this is your R2. and at the end of the R2 it goes to the ground. Allah. Okay, here it goes to ground. Next, what will happen? It meet to the gate terminal. So here is your gate terminal. So next, drain. Okay, let's leave this as it is first. Okay, we don't do anything about the hybrid pi model. Okay, this should be your hybrid pi model. This area should be your hybrid pi model. Okay, hybrid pi. Okay, so we leave that first. Okay, let's go into your drain. Okay, the drain, what will happen to the drain? The drain will have one terminal there. I mean one junction. This is one junction. This is the drain terminal. And then what will happen? One will go to the RD. It will have RD. And another end of the RD, it will go to ground. Next, from this junction, we have another one which is V out. So this is your V out. And usually another V out should go to ground. It is not written there. So this is positive. This is negative. Alright. So how about the hybrid pi model? So hybrid pi model, you just put this structure. Okay, just include this structure into your circuit connection. So now let's include that. So now include that. So we're gonna have the G is already written. So then we're gonna have the S. Here is your source terminal. So source, you can see for the source terminal, it slightly go to the ground because RS has been removed. So source will go to ground. Okay, source goes to ground. Next, we're gonna have the drain. Between the source and drain, we're gonna have transconductance, which is GM VGS, right? So we're gonna have VGS between the positive and negative of source terminal. Next, between here, we're gonna have RD. Because they didn't say the RD is infinity or not infinity. Alright. So in this case, we just include the RD. Okay. Alright. But then don't forget to write where is your input impedance and output impedance. So input impedance is before R1 and R2. So before R1 and R2, you write the input impedance. And then output impedance is after RD. Here is your output impedance. Okay. Okay, so next, let's go to the alright, how to find the value of input impedance, the value of output impedance. Okay, the value of input impedance and the value of output impedance and the voltage gain. What is the voltage gain? Alright, so I think by right, this is same. If you understand well your BJT AC analysis, you can do this MOSFET AC analysis as well. So input impedance, you can look at this part, right? So it's include R1 and R2. And in this case, your R1 and your R2 is in parallel. So R1 and R2 is in parallel, right? Next, your output impedance. So our output impedance is on this side. So if you look here, so inside your calculation must include RD and meaning RD, which is resistance at the drain, and the internal resistance just now from the hybrid pi model of small RD. Okay, so both of this connection is in parallel. So RD parallel with capital letter of RD. Okay, next, usually RD is in very large. So how you want to know if your RD is large or not? If the value of RD is 10 times of RD. If this value RD here equals to 10 times of resistance RD capital letter, so meaning that you can neglect this. Boleh abaikan. You can neglect this. So it means that your RD is too large. So it will become open circuit at this particular part. So in that case, your output impedance will become only RD. Okay, will become only RD. Alright. Okay, next, how to find the voltage gain? So gain, we know when we said about gain, it must be the voltage output. The voltage output divided with the voltage input. Right? Voltage output must divided with voltage input. Okay, so meaning that what is your voltage output? This is your voltage output, which is V out divided with V in. V in. Okay, so what is your V out? So V out same as our BJT. So V out is voltage at this area, right? And if you can see, the arrow is going downside, but we want to find the voltage on this side. So it will be negative GM VGS. Okay, negative GM VGS, and multiply with RD, all the resistance. So in this case, Z out lah, multiply with your Z out. Okay, so if your Z out is, it depends the value of Z out. So Z out either RD parallel with RD, or Z out equals to RD. So it depends. Okay, this is depending on what is your RD value. Okay, so it's actually negative GM VGS multiply with Z out. So this is the value of V out. Okay, divided with your V in. So V in is equals to what? V in is equals to your VGS. So in this case, we can remove our VGS, right? VGS and VGS can be cancelled to each other. So it's only left behind negative GM Z out only. Okay, negative GM Z out. So if let's say your Z out is equals to, RD parallel with RD, so meaning that your GM, your AV, this is your AV, okay, meaning that your AV will become negative GM RD parallel with RD. But if your Z out is equals to RD, in the case of your RD equals to infinity, meaning that your AV is equals to negative GM RD only. Okay, so it's easy, right? So it's easy, and it's straightforward. Okay, because we have discussed this in your BJT AC analysis. Okay, right. So now let's continue to our next example, example number 6. So in this example, it's given to us the circuit, and the circuit shows an amplifier. Right, where's my laser? Okay, here. Alright, the circuit shows an amplifier constructing using an EMOS, and there are specs that given to us, which is the value of K, the value of VGSTH, which is the threshold voltage, and the RD when the RD is infinity. So when the RD is infinity, of course, things that you should come in mind, which is regarding on the hybrid pi model. So therefore your hybrid pi model will gonna be yeah, okay, there, here's my pen. So your hybrid pi model for your AC analysis, so this will gonna be your S, so this is your transconductance, so this will gonna be your drain, and yeah, that's all. You don't have to include the RD because your RD is infinity, right? And K, what's given to us, the K, so K you should know that this actually comes from the value of, or the equations of, ID when ON, which is on condition, so VGS on condition minus VGSTH, which is the threshold, and this is squared, right? Okay, so here are the formula that you should know and you should familiar with. All right. Okay, so next, what are the question asks us to find? The question asks us to find the transistor using the graphical approach. So we have to draw the graphical to get the value of IDQ and VGSQ. So first of all, to get the value of IDQ and VGSQ, we need to analyze this circuit as DC analysis, right? So the transfer curve has been provided to you. So when we said about transfer curve, you should know it is actually this one. Okay, the quadratic. This is the quadratic graph. Okay, where this graph, the equation is. This is the equations of the graph. ID is equals to K VGS minus VGS-TH, the threshold squared. And K is given to us as, what is the value of K again? 0.12 milli. K is 0.12 milli. VGS is based on the value, and VGS-TH is given as 5 volts, right? Okay, 5 volts. And this is good. So you don't have to calculate anymore because this is provided to you. But if this is not given, if this is not given, then you have to draw. How to draw this? Okay. How to draw this? You should know, yeah, it's by drawing the table. Okay, by drawing the table, and you plot the value of VGS here and the value of ID, and the value of VGS should start from the value of the threshold. When it is 5, so of course your ID is 0, so of course it's 0. And then when it is 6, 7, 8, 9, and up until, my suggestion is you follow the value of your VDD. So in this case, your VDD is 40. If it's too much, perhaps you can stop until 20 if it is too much. All right. Okay, so next, so the transfer curve has been given to you. What you need to have is you need to have the KVL. So now let's look at the circuit again. Okay, so here is the given this circuit. So when it is a DC analysis, of course, your capacitor will become open circuit. So this will become open circuit. So meaning that it's gonna be removed. This will gonna be removed. So left behind only the center of the circuit. So when you look here, this is a voltage divider. So of course we can separate the gate and source, drain and source. So we can redraw the circuit to be, okay, because you will need to know how this equation is produced. All right, so we can redraw the circuit. This is your VDD, okay, and this is your R1, okay, this is your R2, and then this is your gate, all right, and then this is your RS, and all of this is grounded, right? And then at this particular part, you're gonna have RD. This is your RD, and then you're gonna have VDD again. Okay, so if you look at this area, okay, this is actually a Thevenin, where we can actually simplify this, which we can find the value of voltage VG at this particular terminal, at this gate terminal. So how to get that? You're gonna be VG, which is this, yeah, this voltage. VG is equals to R2, the resistor across that voltage, R2, R1 plus R2 multiply with the VDD. Okay, and from here you will get the value of VG. All right, and your circuit will then can be drawn as such. This is R1 parallel with R2, and then this is your VG, and then okay, this is your RS, Okay, or if you don't want to include R1 and R2 also, okay, because we know there's no current here. Ig is equals to 0. So when your Ig is equal to 0, so of course R1 and R2 will not be included. Okay, will not be functioning at all. So of course the voltage here is actually this voltage Vg. Okay, so it's better to understand that way. All right, and then across here you were gonna have VGS, don't forget about that. And then current that will passing through this resistor will gonna be IS. And always remember from our previous class, we know your IS is equals to your ID. So this is equals to ID. So can we write the KVL now? Yes, right? So what is the equation for your KVL? Your KVL will gonna be Vg voltage here is equal to VGS plus, okay, VGS plus ID RS, right? VGS plus ID RS. So from here, what is the value of okay, so from here we need to be, since that the value of VGS we don't know, okay, and the value of ID we don't know, but we know the value of VG, so therefore the equation can be rewrite as VGS is equals to VG minus ID RS. Okay, all right, I hope you are very clear with this. So now based from this equation, we want to draw, or we want to plot the load line. Okay, so load line, we know load line, there are two things that we need to draw the load line. Load line is always a straight line. So to draw a straight line, we need to get 2 points. One point at your y-axis, another point at your x-axis. So to find the point at your y-axis, we're going to be when your VGS is equals to 0. So when your VGS is equal to 0, okay, based on this equation, so these are the equation, right? Okay, so this is the equation, all right? I have wrote it here. So when your VGS is equals to 0, okay, we will get the equation, the ID will then become 18 divided with 0.82K, and we will get 21.95 milliampere. So when you get this value, okay, look back into your graph, find where is the value of 21.95. Okay, so the value of 21.95 will be around somewhere around here. So this is 21, this is 22, so 21.95 is somewhere close to 22. Okay, so this is your 1 point. Next point is when your for this to find this is when your ID is equals to 0. So your ID is equals to 0, so definitely all of here will become 0. So therefore your VGS will straight away equals to 18. So once you know the value of 18, so you look at your x-axis, find the place where is 18. So 18 somewhere around here. So it is going to be here. So use your ruler, draw your straight line. Okay, I don't have a ruler, so I am just predicting. Okay, so therefore you will get intersection of this particular part. So that intersection, okay, this intersection, okay, you get the value of your x-axis, the value of your y-axis, okay, somewhere around here. Okay, get the readings. Okay, that readings will be your, this one will gonna be your IDQ readings, and this reading will gonna be your VGSQ, okay, VGSQ reading. All right, so this is the way. All right, okay, so we got the value is IDQ is 6.7 milliampere and our VGSQ is 12.5 volts. So this is not finished yet, because the question asks us then we need to draw the hybrid pi AC equivalent circuit at mid frequency. So at mid frequency, what will happen to your capacitor? Our capacitor will become short circuit. So this capacitor now will become short circuit. This will become short circuit. This will become short circuit. So when this becomes short circuit, what will happen to your RS? RS will be excluded. Okay, because all the current will flow into your capacitor and avoid from passing through resistor RS. Here also we're going to be short circuit. And next is your DC source. So your DC source will become ground. Alright, so when we want to draw, you start your drawing from here. So you're going to have VS, you're going to have RC. Okay. Okay, so this is your VS. Please don't forget to label. And this is your RC. Next, this will become straight line, short circuit. You're going to go to this junction. So at this junction, it will go to R1 first. So you will go to the R1. Okay, so at this junction, it will go to R1. And another end of the R1, it will go to the ground. Okay, next, another path is at the R2. R2, and then another one, it goes to another end of the R2, it will goes to the ground. So you can see here, R2 also will go to the ground. Next, what will happen? It will go to the gate terminal. So this is your gate terminal. So your gate terminal, okay, hybrid pi model, okay, we'll say this is your hybrid pi model. Okay, so this hybrid. So this structure is always fixed as what we have learned and I have been taught to you. Okay, so this is fixed. Alright, so please remember this. Don't mix up with the BJT hybrid pi model. Alright. So next, where's the slide just now? Okay, so you are going to have VGS here. This is your gate. This is your source terminal. Alright, your gate will going to be positive. Your source will going to be negative because your source is connected to ground. Next, this is your drain. So your drain, we're going to have GM VGS. It is no longer GMV pi. It is GM VGS. Why VGS? Because the voltage across that is the VGS voltage. Okay, you're going to have drain terminal. And what will happen to your RD? What will happen to your RD here? As the question said, RD is infinity, so meaning that it will become open circuit. So no RD should be draw here. Okay, there's no RD here. Okay, because your RD is, sorry, small letter RD, is infinity. Right. Next, what will happen next at the drain terminal? Okay, we're gonna have RD, this resistor. So there you are. Here are the resistor of RD, and then you're gonna have RL. Okay, we're gonna have RL, and across RL we are measuring the output voltage. So this is the RL, and across RL we are measuring the Vout, output voltage. This is positive, this is negative. And don't forget to label your impedance, output impedance, and output impedance. Sorry, this is output impedance and this is input impedance. Next, we need to find the value based on the questions. They ask you to find the value of GM, the value of Zn, the value of Zout, and the value of AV. So GM, always remember the formula for GM is 2K. There are two formulas, right? 2K VGS minus VGS TH, the threshold voltage. Alright, okay. So K is already given to us. VGS, what are the value of VGS that we need to use? So the value of VGS that we need to use is based from your DC analysis that you have determined earlier, which is VGSQ, 12.5. Alright, so put it as 12.5. This is 12.5. K is the given from the questions. VGS, we're going to be 12.5. VGS-TH is the 5 volts. So you put inside this equation, and this is supposed to be minus, yeah? Put it as minus. We will get it as 1.8 milliampere per volt. Okay, next is our input impedance. So input impedance, you look at this direction. So input impedance inside of our calculation, we're going to be R1 and R2. And our R1 and our R2 is parallelly connected. So R1 is how much? R1 is given as 22 milli, 22 mega. So 22 mega, this is 18 mega. So you will get your answer is 9.9 mega. In exam, don't forget what is mega. Mega is 10 to the power of 6. Alright. Next, what is your output impedance? So output impedance, you look at the arrow. Output impedance is at your RD. So straight away it is 3 kilo because we don't have small RD is not included. So straight away your output impedance is your capital letter of RD resistor. Okay. Next, we need to find the value of AV, which is the gain. The gain. So we know gain is voltage at the output divided with the voltage at the input. So what is the voltage at the output? So voltage at this output, this is our output, right? This is our output. So to find the voltage of our output, we're going to be negative GM VGS. Why is the reason negative here? Because same as what I has explained in BJT, because of the opposite directions of your transconductors. Then you need to add the negative part. Okay, so negative GM VGS. Okay, negative GM VGS. Alright, multiply with the output impedance. Output impedance. Don't forget we have another resistor of RL, because we are measuring the output voltage at the RL, across RL. So across RL, at the output voltage, we have RL. So how we need to include the RL inside our calculation. Next, you need to consider how your output impedance and RL resistor is connected. Okay, so it is parallelly connected. So your output impedance is parallel to your RL. Okay, there you are. And then we need to divide with your input voltage. What is our input voltage is equals to VGS. So divided with VGS. So based from here, we can cancel out the VGS. So therefore, left behind only negative GM Z out parallel with RL. So you replace all the equations, all the values for this equation, you will get the answer is 4.15. So there's no unit for gain, but if the question asks you to convert into decibel, don't forget the process is same as what you have been taught in BJT chapter. Multiply 20 log 4.15. So you will get the answer in decibel. Alright, clear, yeah? Okay, so now let's look at example number 7. So example number 7, the K is provided to you as 0.5 milli. The threshold voltage is 2 volts and the RD is still infinity. So you don't have to draw the RD. So determine the IDQ and VGSQ using the graphical method. So you need to use the graphical methods in this. But what are the difference between example number 6 and example number 7? Example number 6, if you realize the transfer curve, this curve has been provided to you. This is the transfer curve has been provided to you. Whereas in your example number 7, the transfer curve is not provided to you. So how you want to solve? You need to draw your own transfer curve. Okay, so how to draw your own transfer curve? Remember, the equation for your transfer curve will gonna be K VGS minus VGS TH, right? Squared. Alright, so what is K? K is given to you, which is 0.5 milli. What is VGS? We don't know because this is the value from the graph later on. What is VGS-TH? VGS-TH is 2. So 2. Next, we need to draw the table. Okay, so it's quite a long process, but bear with it. Okay, VGS, and this is the value of ID. So VGS value, you don't have to start from 0. Start from the value of threshold, which is 2. So definitely lah, when you substitute inside this equation, okay, you will get at 2 volts, okay, the value of ID, of course, it is 0 because of why? 2 minus 2, we're going to be 0. 0 multiplied with 0.5 milli, we're going to be 0. So 0. Okay, so next, 3, 4, 5, 6, and so on. Okay, alright. So sometimes our suggestion usually you draw up until the value of VDD. But if the value of VDD is too large, like say 40, 20, draw up until 10 or 15 is also okay. Alright. And you can choose your increment properly lah. Perhaps you can increase 2, 3. Okay, you don't have to do one by one. Okay, the detail that the smaller the increment, the detail of your transfer curve will gonna be lah. Next, when you have all the value, you can plot your transfer curve. So this will gonna be your VGS. This will gonna be your ID. Alright. So your VGS start with the 2 volts. So this is your 2 volts. Next, when your 2 volts, the value of ID is 0. Next, 3. Okay, what 3? So you find the value, and then 4. Okay, get the value, get the transfer curve. So this will gonna be your transfer curve. Next, once you have completed your transfer curve, you need to do the analysis of your circuit. Okay, the analysis of your circuit. Remember, for your circuit, we need to get the value of VG. Okay, we need to get the value of VG. This is the value RS. This is your RS. And okay, so how to get this value of VG? Always remember, we need to consider R1 and R2, which is parallelly connected. So VG is equals to R2 over R1 plus R2 multiplied with the VDD. VDD is 18. Okay, so R2 is 2.2 mega over 2.2 mega plus 4.7 mega. Okay, multiply with 18. Alright, so you calculate to me the value. Okay, this will gonna be your VG value in volts. Alright, next, what you have to do, you need to perform the KVL equation. So the KVL equation will gonna be VG is equals to VGS. Don't forget, we always have the VGS voltage across gate and source terminal. Okay, VGS plus, so the current that is flowing through the RS resistor is IS current. So IS is equals to ID. So here we're gonna be ID RS. Right? So VG is from the value that you got just now. Okay, how much voltage? VGS we don't know. ID we don't know. RS. ID also we don't know. So from here, you rearrange the equation to become VGS is equals to how much the value of VG. Okay, this is from the VG value. Okay, plus minus ID RS, right? Okay, next, because our objective, we want to get the load line. We want to get the load line. So at this particular point, remember, this is when your VGS is equals to 0. So based on this equation, you find the first point. So the first point is when your VGS is equals to 0. What is the value of ID? Find the value of ID. Next, our second point. Here is your second point. This is your second point. So your second point is when your ID is equals to 0. This is ID equals to 0. So you put here ID is equals to 0. What is the value of VGS? So usually VGS is equals to your VG value lah. Alright, so you will gonna mark the value there. Then you can draw the straight line. Once you got the straight line, you will find the intersection, which is the intersection between the load line and the transfer curve. Then identify what is the value of VGSQ, what is the value of IDQ. Alright, so then you got these two answer. Next, you need to draw this mid equivalent AC circuit. Then this is your circuit, so all your capacitors will become short circuit and your DC will become grounded. Okay, so this will become short circuit, RS will no longer included. So this is your AC equivalent hybrid pi model circuit. Okay, next you need to find the, of course lah, you need to find the input impedance and output impedance. So you look at your circuit AC equivalent, where is your input impedance? So if you look here, your input impedance is R1 and R2 and it is parallelly connected, so you count, you will get the value. And output impedance, your output impedance is before your RL, so it is straight away, the value is only RD, so RD is 2.2 kilo ohm, so you don't have to calculate. Next, you need to find the voltage gain. So voltage gain is always output divided with your input. So output, okay, is negative GM VGS, right? And the output impedance, okay, now you have to take into consideration your RL resistor as well, and RL resistor is parallel to your output impedance, so Z out parallel with your RL. Okay, and what is your input voltage? The input voltage, where is your input voltage? Here is your input voltage, V in. So our input voltage is equals to the value of VGS. So VGS is here. So you can cancel out your VGS. So left behind only this. So you substitute the value, you will get the answer. However, we forgot to calculate the value of GM. So the value of GM, we can use this formula, right? Which is 2K multiplied with the total of VGSQ minus with the VTH, the threshold voltage. So we have all this value. What is the value of VGSQ? VGSQ based from the one that you have calculate in, sorry, this is example number 7, right? Okay, based on the graph that you have got it here. Okay, VGSQ. All right, so you got this value minus with 2, okay, multiply with 2 and 0.5, which is the value of K. Then you get the value of GM. Once you got the value of GM, you can substitute into here, then you can get your voltage gain. All right, clear? Yeah. And for the feedback bias, okay, so this is just for your reference. This will not be included into your final exam, so you don't have to worry about this. All right. The calculation of the input impedance and output impedance might be slightly different, so this is just as for your knowledge. You don't have to worry, this will not be covered into your final exam. All right, so we can omit example number 8, example number 9, and yeah, by that I think we finished covering all the AC analysis, DC analysis for our MOSFET transistor. So on our next class, we will focus on the OP amp amplifier. Right? Thank you so much.